So, welcome one and all to the weekly discussion session for the physics of the nanoscale devices NPTEL course. This is a discussion session for week 9, where we shall be focusing on the contents that are primarily from the lectures in week 10 of the course. The topics that we shall be discussing today will mostly pertain to the transport of carriers in a ballistic MOSFET. So, before we begin, I'd like to ask the live participants if they have any questions or queries based on the assignments
No,
or no queries. Okay, good. All right.
No, sir.
So, in that case, let's dive right in. So, one more clarification from you guys. You are able to do the assignments well enough, right?
yes, sir.
All right, good. So, and whatever I'm saying here is at least marginally useful, correct?
Yes,
Yes,
sir.
sir.
Actually, just
Huh.
I missed week ninth assignment.
Oh,
Don't know
okay,
the time, na. That's why. But sir,
okay.
top eight assignment will be means marks will be awarded in
Yes,
top eight assignment,
yes,
na.
yes.
Because it is due to the that the coursework, other coursework
No, no,
subjects.
that is fine. That is fine. You don't have to give me
Okay.
excuses. Like, what I'm asking is
Yes,
if,
sir.
like, okay, so this was essentially not to gauge your performance, it was to gauge my performance. So, to see if whatever
Okay,
I'm
sir.
saying is at least, marginally useful to you guys. So, as long as two people are saying yes, I'm assuming it will be useful for the others as well. Yeah. All right. So, let me just check if, yeah, recording is happening. Yeah, so let us begin with today's discussion. As I have been telling, that is, yes. So we are looking at ballistic. Oh, yeah. No, please. I have not shared my screen. I just realized that. Uh, you know what? Let me just. Yes, somehow that doesn't show up. I hope the board is visible now.
Yes, sir.
Yeah, good. Thank you. So, yeah, so we are looking at ballistic MOSFET. So, uh, now just a recap. What is the chief difference between a conventional MOSFET, a normal MOSFET, and a ballistic MOSFET? Uh, Kamal, Ichanshu, can either of you tell me?
What, sir?
Like, what is the chief, like, most important feature of a ballistic MOSFET?
What to say? Minimum loss.
Minimum loss. Okay, like
In the channel.
I was actually asking for much more elementary things. So essentially, ballistic channel,
Okay, sir.
ballistic MOSFETs are short channel MOSFETs. So this is to the order of 10 nanometer, no more than that. So I mean, typically it is less than that. Now, so for ballistic devices, based on what we have discussed so far, what, let me ask it this way. What are the two most important equations for a ballistic MOSFET?
So conductance.
Conductance or something else? It is. Oh, sorry. Yeah. Yes, yes, yes. I know that. Yeah. So the transport characteristics. Let us just write it as the transport characteristics of a ballistic channel. So the two equations that you guys might have seen like very early in this course, maybe in week 3 or week 4. Those are these N and I. You guys
Okay,
familiar with
like number of
this?
electrons in the channel.
Yes.
First, we calculated the number of electron in channel, then the current flowing from source to drain.
Yes. So what is N? Like what does it look like? Yeah, so an added point here, we can typically have a 3D, 2D, or a 1D channel in a ballistic device. Why can't we have a 0D channel? Can you guys quickly tell me that? Any guesses? Why am I not including 0D in this list?
No idea.
No idea. Oh, it's quite simple
Sir,
because see,
it's
I mentioned,
one suggestion.
huh?
Solution like it's confined in all three direction. So
Uh-huh.
this short channel effect is not dominant in that 0D system.
Okay, so yeah, I mean, that is, you can definitely say that and you will not be wrong, but the answer is even more straightforward. I've already mentioned that the channel length has to be, like 10 nanometers, which implies
10
that the
nanometer.
channel should have some length. Now, if it's a 0D
Yes, sir.
channel, like the length dimension does not factor in at all. Is that clear? So I need a channel that has some kind of length. So for it to have some kind of length, I will need at least one dimension. Okay.
Yes, sir.
So, yeah. So, primarily, the 2D will be our main focus. However, whatever results you see for a 2D channel, you should be capable of generalizing it for the 1D and the 3D channel as well. So, uh, so if you guys have your notes or something, can you tell me what this N equation is?
Integration
Uh huh.
dE into F1e plus F2e by
Uh
2
huh.
into dE.
By 2 into another D. Acha,
Sir,
okay, DE, okay,
हाँ,
integral. Fine, fine, fine. Yeah. So this is, yes, D of E into F1 of E plus F2, oops, of E divided by 2 DE. Is this correct?
yes, sir.
Wonderful. Yeah, this is correct. So, so what is I?
So 2q by h
Uh-huh.
integration
Uh-huh.
um, gamma e into pi by
Uh-huh.
2 into dE uh,
Uh-huh.
into f1 minus f2 into dE.
Uh-huh. Okay. Very good. This is also correct. However, we shall be using the more convenient representation, because we shall no longer be explicitly calculating the broadening and density of states
Yes, sir.
for these systems. So what
We
we
can
shall
use
do is,
any number
yes,
of modes.
very good. I mean, that's actually nice. Good. So, okay, keep this in mind. If you guys can remember these things that you are telling me, you are good to go for the course. Okay, like for the previous week's contents. Like these are the things you are supposed to remember. So, as long as you are remembering them, things are fine. This is also to the people who are listening to the recorded version of this discussion. So, we can write it as this, correct?
Yes, sir.
Minus f2 of e dE. So these are the two equations that we shall be concerning ourselves with. So for the purpose of today's discussion, I shall call this equation 1 and equation 2. Okay. So now, uh, yeah. All right. Now, if you remember in our previous weeks, like previous weeks meaning like in the past weeks, like occasionally we have taken to calculating the number of modes, for several special conditions and what to say, like different geometries and so on and so forth. Like we have done those things. However, here we shall not be doing the explicit calculations. What we shall be more concerned with, more focused on, are the like the trends, the uh, dependencies, and the variations that we shall see. Like we'll essentially want to know how the mode will vary with, say, the energy level, or how the what kind of terms will appear in these integrals. Okay, so as I've told you before, 2D channels will be our main focus. So remember equations 1 and 2. I shall be calling back to them. So yeah, to the next board. So yeah, uh, what should we what should we say? Yeah. So now consider a 2D ballistic MOSFET. So first, whatever be the channel dimension and anything, how will the band diagram of a ballistic MOSFET look like? A MOSFET, not a two-terminal device, the three-terminal device. So I'm going to try. Yeah, please don't try to describe the band diagram verbally. I will draw the diagram. Just tell me what goes where. Okay. So yeah, let's draw that in red. So I'm saying the band diagram will look something like, yeah, or rather the other way around. vector source. Yeah, and this is the source section, and everything in between here is the channel. So is this diagram correct? Assuming VDS is very small. Any comments?
Sir, no idea.
No idea. Okay. So if we had an, oh yeah, I forgot to mention that. So this is an N MOSFET. Is it an N MOSFET? Yes, of course it is an N MOSFET. So I'm looking at an N MOSFET operating in the depletion mode, not in the enhancement mode. So what will be the profile for like, so what if I'm drawing the conduction band, valence band diagram for the source, channel and drain for an N MOSFET, just tell me where the Fermi levels will be present. This is the drain, channel and source. So if it is an N MOSFET, what kind of a material will the channel be? N MOSFET in the depletion mode. Like this thing you should know, even independent of this course. Will this be an N-type material or a P-type material? The channel. General MOSFET, not ballistic.
Sir, N type.
For an N MOSFET that is operating in the depletion mode.
No, sir, for P1.
Huh? Like I'm asking for an N MOSFET. So what will the channel material be? It's going to be a P-type, correct?
Yes, sir.
So the Fermi level is going to be somewhere over here. Channel and drain are, sorry, source and drain are going to be N-type material. So its Fermi level is going to be up here. So when I bring these three together, just look at the conduction band profile. So at equilibrium, how is the conduction band profile going to look like? It's going to look something like this, correct?
Yes, sir.
Yes. So now, if I were to apply some kind of a VGS, so essentially my gate is over the channel, my drain is here, and my source is here. So as long as VD and VS are roughly equal, these 2 points will be on the same level. Now, if I were to apply some kind of a VGS, what will happen to this part of the curve? Let us say I'm applying a positive VGS. VGS greater than 0.
So it will bend downwards.
Yes. So essentially what will happen is this thing will start bending downwards. That is what I've
Yes, sir.
drawn here. Is that clear now?
Yes, sir.
Alright. So this diagram is important because like our conventions will be based on this. So this is true for any MOSFET, ballistic, what to say, like diffusion transport, ballistic transport, whatever you are considering. Essentially, this is the kind of a band in like energy profile I need for transistor action. So it's like not dependent on the geometry of the device or anything. This is the kind of device that I want. So whatever geometry I choose, ultimately this is the kind of a band structure I would like to implement using whatever device I choose. Okay, so this comes directly from the device definitions. Like this comes from a conceptual level. This is not due to the physics or anything. Like this is the kind of an energy distribution I theoretically want. So this is what the band diagram will look like. So because of a positive VGS, and here, yeah, I'm also assuming VDS is small, just so that this diagram looks simple enough. So I have my drain level, yeah, apologies. So I have my drain level over here, and I have my source level almost here. So as you can see, the so this is the profile for the conduction band and the valence band. Since we are looking at electron transport, we will be more concerned with the conduction band. So this is, I'm also saying the like uh, apologies, just 1 second. Yeah, yeah, sorry for the disturbance. Um, where was I? Yes, VDS is small. Now this is the conduction band profile. So let me also indicate that this is the conduction band profile. All right. So the band minimum, or essentially the band edge of the conduction band, varies like this across the three like regions of my device. So there will be a point over here somewhere where the energy reaches a maximum value. Okay, so here at this point, energy is maximum. Now, what can you tell me about the electric field at this point? Any guesses? Okay, I'll give you three options. So I'm saying the electric field E vector, like it will it be greater than zero? Will E vector be less than zero? Or will E vector be zero? Which one is correct? Again, yes, you can pick anything at random.
Okay.
Greater than
So
zero.
electric field greater than zero.
Greater than zero. All right, good. Okay, fine. So let us see what it is. So, I mean, I'm also glad that both of you said the same answer, so I can give you the same explanation. So, all right, moving on. So, what is electric field? E is equal to, yeah, so notation will get slightly confusing here. So let me just write it like this to distinguish that this is the electric field and not the energy. Okay, so this is what, and you know what? Let us call this the x-axis. Let us call this direction along which transport is happening. Let us call this the x-axis. So now, can I write this as minus dou v by dou x cap? Can I write it like this, where v is the potential? Is this correct?
Yes, sir.
Very good. So v is the potential. Now, what is the energy? energy is Q times V, right?
Yes, sir.
Yes, sir.
Okay. Now tell me this. In this energy distribution, this is a maxima point. If it is a maxima point, what will the derivative be at the maxima point?
Zero.
Yes. So at the maxima point, so this is the first thing that you have to remember. At the maximum energy, now you can ask why this is important. I will tell you in a minute. Energy point, E vector is equal to 0. Okay. So let me again draw this graph. So I have a rising line and a falling line, my drain and my source. So I will have this point, which is roughly the maxima. And what I shall do is, I shall identify this point on the x-axis. Okay, so essentially, this is my x-axis. So I'm going to identify this point and I'm going to call this x equal to 0. Is this clear?
Yes, sir.
Okay, so the maximum energy point is from now on in our convention will always be referred to as x equal to 0. So at this point, electric field E vector is equal to 0. When the electric field is 0, what else is 0? Like potential was related to energy. What is the electric field related to?
A charge.
I mean, I'm talking about like a dynamic quantity. Like charge, yes, of course, like electric field is determined by the total charge. I understand what you said. But what quantity, am I hearing something? No. What quantity is determined by the electric field? Let me ask it this way. Like, see, Q times V gives me energy. What will Q times E give me? If I put a Q in front of the electric field, what is Q times E?
Somewhat like velocity, sir.
No, Q times E is the force. See, remember your Coulomb's law. F is KQ1, Q2
To 1 upon
upon.
4 pi epsilon naught divided to
Yeah,
r
so that
square.
is what I'm calling K, 1 upon 4 pi epsilon naught, R12
Yes.
squared, correct? Or R21 squared, however you write it. Square is there, so it doesn't matter. But let us be precise. Let us write it as R21 squared. Uh, Now, if I want to find the electric field experienced by charge Q2, what will I do? This is a vector quantity, so this will be R21 cap. So the electric field will be KQ1 upon R21 square, correct? Like this is the electric field as experienced by the charge Q2.
Yes, sir.
So that's essentially what is happening. If I multiply this by a charge, what will I get? I will get the force. Okay.
Yes, sir.
Now that implies Now this is important. So this implies, so this is the 0 point, and so I'm essentially saying that, yeah, let me make the axis marking more clearer. I'm calling this the x axis. So this point is e equal to 0, and I'm labeling this as, let me use this, labeling this as x equal to 0. Okay, so therefore at x equal to 0, just one second. Was there any, like, you guys have been able to hear me, right? I did not lose connection or anything.
Yes, sir.
Oh, wait, I lost connection?
No, sir, I can hear you.
Okay, okay, fine, fine, fine. Yeah. Yes, yes, yes. I know I'm presenting. Yeah. So, what was I saying? Yes, at x equal to 0, this is important. Force on the electron, or force on the electrons, is 0. Now, what does ballistic transport mean? What is the meaning of the word ballistic?
Sir, when mean free path of electrons
Mhm.
is almost equal to channel length.
Yes, correct. So that is the condition. But do you know what the word ballistic itself means? Like we say we have ballistic missiles and things like that, right? So what is
Yes,
ballistic? The word. So ballistic means that the object that is moving, like we will say an object is moving in a ballistic fashion when the object is
It's like a
essentially
bullet
moving.
like fashion.
Huh?
Yeah, sir, bullet like fashion. It will
Yes,
go from
exactly.
source to drain.
There is no active propulsion. There is no active force being applied on it.
yes,
Is
sir.
that clear? So essentially, when we say that the mean free path is small, or rather, sorry, the mean free path is comparable to the channel length, what we are saying, there are no collisions. Since there are no collisions, no external force is applied upon the charge carriers. Okay, that is
Yes, sir.
equivalent to saying no external force. Since at this point the force on the electrons is 0, what is happening? At this point, ballistic transport has begun.
Yes, sir.
Okay, so so this implies we have ballistic transport. That is why we have been like discussing all of these things. Now, do you understand why the what role the gate is playing in this entire picture? Like originally, let me go to the previous, or rather, let me quickly just illustrate it here. Originally, when no gate voltage was applied, what would have happened? Our band diagram would have looked something like this. Correct?
Yes, sir.
Now, where is the maximum? Maximum will be somewhere over here, in the middle
Yes,
of
sir.
the channel. All right. Now, because of that, what will happen is ballistic transport will actually only begin at the middle of the channel. And in fact, soon after that, ballistic transport will get interrupted. Now, by using the gate voltage, what we are essentially doing is we are shifting this maxima closer and closer and closer to the drain side. Can you see that? So
Yes,
as and
sir.
when VGS increases, this will keep going lower and lower and lower and lower. So the maximum will be somewhere over here. So the x equal to 0 point will keep sliding towards the drain. Because of
Yes, sir.
that, Ballistic transport happens in a greater area of the channel, in a greater region of the channel.
Okay, sir.
Okay, so this is how the third terminal, like previously, whatever we studied as a two-terminal device, the third terminal essentially determines where the ballistic transport begins. So that is kind of the role of BGS, okay, in a ballistic MOSFET. So this is like that is worthwhile remembering, although I don't think there are any questions that directly use that concept. Uh, Additionally, so before we move on from this, there should be some, is there something else that we need to discuss over here? Um, yeah, so like from now on, x equal to 0 implies, so if I'm writing x equal to 0, then that implies we are talking about the peak of the conduction band energy, or rather the band energy. Let us not call it the conduction band energy. Or rather, let us not even call it the peak. Let us just call it the band maxima. That is a more accurate term. So this is the band maxima. What is the band maxima? It is a point where the band energy goes to the highest. So erase. Okay, so this is the x equal to 0 point, and of course band maxima is determined by VGS, like most primarily determined by VGS. Okay, I'll leave that out for now. Like we'll talk about that later. So,
Hello, sir.
Kamal, yeah, do you want to ask something?
Yes, sir. Yes, sir.
Yeah,
So
go
one
ahead.
question I'm getting like, suppose we are applying VGS voltage. So how
Yes.
this shifting? Maybe it will shift toward like source side. Maybe it
But
should.
as long as VGS is positive,
Yes, sir.
this side will keep lowering, right?
Yes, sir. Yes, sir.
So, yeah, of course,
Means
where
it
by
totally
negative
depends on
VGS,
the
the opposite
polarity
will
of
happen.
it.
Yeah, but
Yes, sir.
typically, like in our transistor operation, what is the sign of VGS? VGS is always positive. Okay, so now,
Yes, sir.
like, this should also kind of give you retroactively give you a reason why we consider VGS greater than 0, VDS greater than 0 for like operation regimes of the transistor. Like, why we made those choices. Because, as you can see, this band diagram we arrived at by essentially considering an NPN junction. Like, whatever we have
Yes, sir.
drawn here is not only true for a MOSFET, it is also true for a BJT. It is also true for a JFET. This band diagram picture is true for any kind of a transistor that you can think of. There is going to be a band diagram of this kind, and by some means, I will try to distort this band diagram in a particular direction. So field effect transistors, I essentially do that by the application of an external electric field. So that those are the field effect transistors. In the case of uh, like bipolar junction transistors, what essentially happens is we inject minority carriers into this channel. Like there is no channel per se in a BJT. What we essentially have is the base region. So in the base region, we inject a very large amount of minority carriers. And what we call the minority carrier in the base is actually the majority carrier in the collector and the emitter regions. So there, this distortion is achieved via charge. Whereas in field effect transistors, this distortion is achieved via electric field, or rather an external potential. Okay, so this concept, up until now, the concept that we are discussing is general to the concept of transistors. It is not limited to ballistic transistors, but however, this point that when E becomes zero, ballistic transport begins. So that is a point of added significance for us because we are considering a ballistic transport, like ballistic devices with a ballistic channel. Okay, so moving on to the next slide. Just 1 second. Yeah, apologies for the disturbance. Okay, this is not good. Why are you not visible? Uh, oh, okay. No, this is severely problematic. Just 1 second. Yes. Yeah, for a second my pointer became invisible. And since mostly when I'm presenting, I look at the display and write without the pointer, I am blind. So, yeah. Now we shall be looking at the current and voltage expressions for a 2D device. Current, not voltage, current and charge. Why call it expressions? We know they will be integrals, so let us call them current and charge integrals. Okay. Now, what is the added condition? We are looking at a 2D ballistic channel. So it's a 2D channel. So what are the things we know about a 2D channel? Okay. Why is this happening here? Somewhere in the middle of the screen, my yes, yes. So for a 2D channel, what is the density of states for a 2D channel? Any guesses?
Means equation, sir.
Yeah, the density of states, the expression.
Okay.
Is this correct? Am I correct in writing this?
Yes, sir.
All right. So this is independent of the energy. Remember these expressions. These will come in handy. There
E
might
raised to
be,
zero
huh?
means it's constant for
Yes.
2D.
E raised to the power zero. Yes. So that is also, yeah, let us write it here. So it is independent of energy, which is why you will see many of the expressions will actually be uh, straightforward, independent. Oh, yes. Now this has become a part of the video, so everybody knows I cannot spell independent. Independent, yeah, of energy. So from now on, when I write E, I mean the energy here, okay? So just for clarification's sake, in the previous slide, whenever I wrote E, I was referring to the electric field. That is why I wrote it as E vector. Over here, that is no longer the case. When I'm writing E, I mean the energy. Please remember that.
Okay, sir.
All right. So now let us look at the charge. What will n be? Like in general, assume that VDS is 0 and source and drain are of the same material. Then what will happen to equation 1? For clarification, this will be d to d of E into
F1 plus F2 by 2 DE.
yes f1 plus f2 by 2. I mean, more precisely, this quantity here will not just be d to d, it will also be d to d into W, width of the channel. I hope you guys remember that.
Yes, sir.
Okay, so what we write here, what we use in the integral is actually d of e. D of e, like for 1D channel, is just d1 d of e. But for a 2D channel, it is d2d into W, and for d3d, it is d3d into the
Area
area of
into.
cross section.
Yes, sir.
Okay, so dE. Now, if VDS is 0 and source and drain are of the same material, then what will happen to this term? Like, will F1 and F2 be different if VDS is 0 and source and drain are of the same material?
No, sir. It's the same.
Yes. So what will this quantity then become? It will just become one Fermi function.
Yes, sir.
Yes, sir.
Okay.
Right, sir.
So now this is just an assumption. Like I'm not saying this is what we will always do. I just want to show what is happening. Again, our point here is not to calculate exact quantities. Our aim here is to understand what kind of terms appear where. So I'm assuming VDS is equal to 0 and source and drain are same material. So now this is an assumption. So under this assumption, N will become, oops, let me change color for the sake of consistency, which implies N is now equal to integral. Let me just substitute the value here, M star pi h bar squared into W into, so uh, yeah, so what is the Fermi function? It will just be replaced by one Fermi function. So this is 1 divided by 1 plus exponential E minus EF E minus EF upon QBT, correct?
80. Yes, sir.
And times d, of course, it's an integral. Now, since this quantity is occurring here, let us replace it by eta. So, essentially, defining eta to be E upon QBT, what we shall see is then dE will be d eta KBT. So, we will have this is equal to, and let us divide this expression by W on left and right. So if I divide it by W, then what will this quantity be?
Number of sorry, number of electrons per unit width.
Will it be per unit width or will it be, see, now this integral here actually takes into account the channel length also, in a sense. So when I divide by W on both sides, what I will actually have is the surface charge density. See, if you remember your old derivation, we take the source, we take the drain, correct?
Yes,
And we
sir.
have that channel of length L in between, and we assume that there is equilibrium between here and here and here and here. That is how we arrive at this charge expression, this integral over here. That is how we arrive at. Okay,
Yes,
so
sir.
already charge has one inverse length dimension because this L is already absorbed over here. So this itself is charge per unit length.
Okay, sir.
Okay, so when I further divide it by W, what we will have is the surface charge density.
Surface charge density.
Okay, so when we have the surface charge density there, so Ns can now be written as, let us, write out the like terms in the integral. So that will be m star kbt divided by pi h bar squared. Okay, into 1 divided by 1 plus exponential eta minus eta f, where eta f is eta corresponding to the Fermi energy, d eta. Is this correct?
Yes, sir.
Now, further, we can, perform this integral. I'm not doing the integral, like, I mean, I'm sure you guys can do this. I'm just going to write the final answer. It's going to be m star kbt divided by pi h bar squared into natural logarithm of 1. Yeah, so this essentially goes from 0 to infinity. That is the limits of integration. So this goes from, yeah, so this can be written as 1 plus exponential eta. Will it be exponential eta f or exponential minus? No, it will be exponential eta f. Yeah. Yeah. There may be a minus sign here. I'm not very confident. I do not want to do the integral. What I want to emphasize is, or wait, the f. So that will be log of that and multiplied by, so dt. So t is going to vary from 1 to, as the thing goes to infinity. So this quantity will be uh, yeah, so it goes higher and higher and higher. Just 1 second. Let me just confirm what the answer is in order to avoid any further confusion. So just give me a second. Yes. New recording. Yes. Yeah. Yeah. Sorry for that. God in heaven. If I turn off your notification, you give me a notification to ask if I should allow notifications. You can't win with Google. Uh, so yeah, coming back, like after this derivation, so this integral gives us this quantity, and now that can be written as natural log of 1 plus exponential of eta f. So yeah, in that case, this integral is technically not supposed to be 0 to infinity. Yeah, so that is where I was making a mistake. In general, this integral is represented from minus infinity to infinity because technically speaking, all energy values should be taken into consideration, even the ones in the valence band. So, like if we are setting the zero level at the bottom of the conduction band, then the bottom of the valence band will be a very low energy compared to that. So, it is a good approximation to treat it as minus infinity. Therefore, yeah, we have this expression here. Uh, just let me write this as clearly as possible. So, this is natural logarithm of again. Yeah, this is yes, natural logarithm of this quantity. So now this we are going to call the effective density of states in 2D, and this is the Fermi integral of order 0. Go back to the Fermi integral lectures or slides, or if you have made notes, you'll see that this expression is exactly equal to f0. Therefore, for a 2D channel, Ns is N2D under this condition. Under this condition, F0 eta F. Is that clear?
Yes, sir.
Now, even if this were not true, what will happen is it is going to be, see, this constant will always come out because this effective density of states essentially comes from a change in variable going from E to eta. That will always happen. And in a 2D channel, this will always jump out. The only thing that may not change is the source and drain Fermi levels may be different, or the source and drain might operate at different voltages. Other than that, whatever derivation we have followed through is essentially the same. So, whenever I am looking at the charge carrier density in a 2D channel, it will depend on the Fermi integral of order 0. So, this is the Fermi integral or the Fermi Dirac integral in integral of order 0. So whenever we have a charge integral, f0 will occur in the case of a 2D channel. Now tell me what Fermi integral will occur in the case of a 1D channel. Just make the appropriate, just figure out what will change and guess what will happen. Ah, oh, wow. Have I been? Okay. So, yeah, did you guys hear what I asked you?
Sir, can you repeat? Actually,
Yes.
my
Yeah, I
connection is
figured. Yeah,
lost.
you got disconnected. Kamal, you are still connected, right? Okay. Okay. Kamal has raised his hand. Yeah. I can you hear me, Kamal? Okay. I suppose he has some audio issues. Otherwise, he'd speak up. So yeah, Chanshu, I will repeat my question. So over here, for God's sakes, disable. I will go to the browser and yeah, kill all notifications. So be fine. You're not asking. Uh, yeah. So yes, what I was asking is now this is the expression for the surface charge carrier concentration in uh, the 2D channel. There is an effective density of states term, and which essentially takes care of the temperature dependence and a Fermi integral.
Okay, sir.
Okay, now what I'm asking is what will change if we have a 1D channel? What Fermi integral will appear in the case of a 1D channel? Can you guess? Kamal, in case you are unable to speak, you can always type your answer out in the chat. Can you guess it, Shanshu?
No, sir.
See, there is what energy dependence in the case of D to D? Okay, I think Kamal has typed something. Or network issue. All right, it is fine. Uh, yeah. So, in the case of, yeah, D to D, what power dependence of energy did it have? E to the power?
Zero.
And what Fermi integral do we have? F0.
Of order zero.
Yes. So, what will the energy dependence for the 1D density of states be?
Of sir, minus half.
So, what will be the order of the Fermi Dirac integral?
Minus half.
That is all. Okay. Now,
Yes, sir.
just to clarify, going to this week's content, week 10 assignments, you will notice that questions are like this. What kind of Fermi integrals will appear? What kind of Fermi integrals will appear? Is that clear? So whenever such
Yes,
a
sir.
question arises, look at the corresponding integral, substitute the necessary quantities, and just find out what Fermi integral will appear there. And rest assured, what we have solved right now is not an assignment question. That is precisely why I'm solving it. Okay.
Yes, sir.
So this is the logic to follow to solve those questions. Okay. So now this is the charge integral. Let us also look at the current integral. And then we shall look at what is the like arguably the most important quantity for like this week's discussion, and then we will like switch over to some conceptual discussions also. We'll do less derivations and talk about one or two ideas. So now the charge and current integral, yes, this is continuing. Charge and current integral continued. So now, what is the current integral? The current integral is given by integral T of E, M of E, F1 minus F2
into DE.
dE. Wonderful. Of course, there is a factor of 2q upon h bar. All right.
Yes, sir.
Good. So nothing is there. All right. Now, since it's a ballistic channel, T is approximately equal to 1. Okay. Since
Yes,
it's a
sir.
ballistic channel, like, I mean, obviously T has to be close to 1. So let us take it as 1. Again, my aim is not to calculate things here. My aim is to show what is happening, like what kind of expressions arise. Now, what
Yes, sir.
happens? What is M2D of E? I think both of you were present for this. We actually defined the 2D modes in a very concrete fashion. Like it was connected to the width of the channel. Like if I had a 2D channel of this kind of length L and width W, the modes had a connection directly to this. Do you remember?
Yes, sir. Sir, uh, it was W times of root over
Uh-huh. Like yes,
E
you're trying to guess the expression. Forget the expression. Think about what it is. Like
So it
it
was
is essentially
directly
W
proportional.
divided by the number of half wavelengths, de Broglie wavelengths. Lambda de Broglie by 2. Now, what is lambda de Broglie by 2? So, de Broglie wavelength is, yeah, it's not sub B. So, this is dB. So, this is H by P, which is, and what is P? This is H by square root of 2 ME. So, yeah, that's it. We are here. Is this clear now?
Yes, sir.
So I will just, so this is lambda dB. So this by 2, there will be another factor of 2 here. And that divided by W. So essentially what we will have is 2W into square root of 2ME or M star E. M star here divided by, yeah, H is M of E.
Yes, sir.
Okay. So
Yes, sir.
like this was the expression you were trying to guess, right?
Yes, sir.
Ah, so like this is another way of remembering this. This derivation I actually did in one of the previous sessions. You can go look at the. I think that was either week 5 or week 6. So you can go and look at that video. Like all the videos are now like
Okay, sir.
available to you guys. So you can go and see that. So it's going to be something like this. Okay. Now I have my Fermi functions over here. What is the energy dependence of M of E? E to the power?
E raised to half
Yes. So what Fermi integral will appear in the current?
of order half.
Exactly. F half of E. Okay. So
Yes, sir.
whether or not you are evaluating the integrals, whether or not you guys are able to evaluate the integrals, that is fine. I mean, that's a secondary concern. First and foremost, you should be able to identify what ratios of the integrals will appear. Okay.
Yes, sir.
Now, so again, quick question. If this were a 3D channel, what kind of a Fermi integral will appear? So let me quickly
Sir,
type.
of order one.
Order 1.
Yes, sir.
Yeah, you're correct. Good. Yes. So I'm not even going to write that in this slide. Let the people who watch the video benefit from that point. Because that is slightly related to one of the questions in the assignment. So I don't want to like explicitly give it in writing in the slides. So essentially finding the power of energy in the current slash charge integral will allow the identification of the corresponding Fermi integral. Okay,
Yes, sir.
all right. So that is that. Uh, mm, yeah. So let us look at one last thing in this slide itself. I don't want to open a new slide for that, for obvious reasons. So let me just draw a small box to this half. Yeah. And actually, for the first time, like after almost 10 weeks, I'm actually covering the topics on schedule. Amazing. So it's taken me that much practice. Now, consider the case for small bias, small drain source bias. So first, okay, Chanshu, since you're probably the only speaking member in this call, I think Kamal is still with us. Yeah, he's with us, but he's having network issues. So I'm not going to trouble him, which means unfortunately I will have to trouble you. Uh, for a small drain source bias, what region of operation will the MOSFET be in? Will it be in the cutoff region? Will it be in the linear region? Or will it be in the saturation region?
Sir, what does small drain force bias mean?
So yes, that's a good question. So let us quickly see what we mean by that. So this is BDS versus IDS. Okay. Now what will these curve like? There will be several curves for different VGS, but typically what will this curve look like? It will look like this. Correct me if I'm wrong. It will look something like this, right?
Yes, sir.
Okay. So now it will be like this. So this is like different VGS. So VGS1, VGS2, VGS3. Ah. So VDS is increasing in this direction. So for smaller values, for lower values of VDS, what region of operation is the device in? which of this is linear, which of this is saturation? Is left linear or is right linear?
So left one is linear.
So for small drain source biases, the device is in the linear regime.
Okay, sir.
Okay. So if your question suddenly says the device is in the linear regime, you should quickly remember that this implies VDS is small. So this is
Yes, sir.
small VDS. That is the linear regime. Okay. So we have that. So for small drain source bias, what is the current integral? Now we can actually write some things. Now we can write I equal to GB because the small bias has appeared. And what is the conductance? It is 2q squared upon h integral m of e
Into
times
Fermi window function.
exactly e dE.
Sir, minus sign will also come uh,
Uh,
for Fermi window.
yes, you're right. So there will be a, let me put the minus here over here. Okay.
Yes, sir.
Ah, so let me just make the minus. Like, thank you for pointing that out. So now remember what I told you before. Like I can also like essentially take the minus sign inside and write this as dou f by dou ef. Correct?
Yes, sir.
If I can write it as dou f by dou ef, then this integral and this derivative become two independent operations. I can either take the derivative and integrate, or I can integrate and take the derivative. Correct?
Yes, sir.
Now, if I integrate for a 2D channel, what will the Fermi integral be? It will be this f half.
Okay, sir.
Correct?
Yes,
Like, I
sir.
mean, that's what we saw, right? And then I'm taking a derivative with respect to E or eta f. In that case, what will happen? If I take the derivative of a Fermi integral, do you remember that property? So this is equal
No,
to.
sir. Right now I don't
Okay,
remember
so
it.
essentially what happens is if I take the derivative of this integral with respect to eta f, the order will reduce by 1.
Okay, sir.
Okay, so for small bias, the conductance G is proportional to F minus half of eta F. Similarly, you can derive the results for a 1D and a 3D channel also. All you have to do is figure out what the definition, what Fermi integral will appear in the general definition of the current, and then go to the this case, the Fermi window will have a derivative of it, so you reduce that order by 1. So essentially, by looking at the energy dependence that appears in the mode function, we can determine what kind of Fermi integrals will appear at all of these points. Is that clear?
Yes, sir.
And that is most of the questions that you have. Like most of the questions that you, like most of the questions in the assignment are going to be like that. All right. Now we are coming
Yes, sir.
finally to the last topic we want to discuss today. We shall be talking about ballistic velocity. Okay, so remember what was the assumption like way back? Now, this has not been discussed today. When we calculated the charge integral, we made a very important assumption. What was that? It is that the charge entering the channel is equal to the charge leaving the channel.
Yes, sir.
Like if you go
The
back to
first or
the
second class, I
yes,
think so.
yes. So it was not first or second class. Like first or second class, we were probably still doing quantum mechanics and density of states derivation. But once we started doing ballistic, the two terminal device in the first or second lecture itself, sir would have mentioned that when we are calculating the charge, we are assuming that the charge moving in is the charge moving out.
Yes, sir.
Okay, now in that case, what is the velocity of the what is the average velocity of the electron in the uh, channel? These are ballistic electrons, implies they suffer no collisions. Electron enters the channel, travels with a constant velocity, like without any collisions. I'm not saying constant velocity, without suffering any collisions, and it leaves the channel. The amount of electrons entering the channel is the amount of electrons leaving the channel, which implies at any point in time, the stored charge will remain a constant and there will
Yes,
be a
sir.
constant current flowing through the channel. So in that
Yes,
case, what can you tell me about the velocity of the electrons?
sir. It will be equal to channel length upon transit time.
Yes, that is one way of saying it, correct. Can you tell it in a more elementary fashion? Like in a more, like, uh, based on known quantities, what have we been discussing so far? Current and charge. Can you tell me in terms of current and charge? Is I by n equal to the velocity or at least the average velocity?
Yes, sir. We have derived some sort of equation.
Yes, you have actually. Yes, you have. In fact, even the transit time derivation comes from this only.
Yes, sir.
Okay, so this is what we do. We essentially divide the current by the stored charge to get a notion of the average velocity. But of course, this is not just the average velocity, this is average of the average velocity. Now, what do we mean by the average of the average velocity? At a finite temperature, every electron will not have the same energy, correct? They will have different energies, like there will be an energy distribution. Therefore,
Yes, sir.
every electron will not be traveling with the same velocity. Different electrons with different velocities will enter, and different electrons with different velocities will leave.
Yes, sir.
So not only are we averaging the velocity over the different electrons, we are also averaging the velocities over the different values of velocities. Is that clear?
Yes, sir. Yes, sir.
So that is why we put this double average symbol. Okay.
Yes, sir.
And of course, this is in the positive x direction because I am only considered concerned with the drain source current. Okay.
Yes, sir.
So this is this quantity. Now, again, let us not go into calculations. I know for a 2D channel, I is proportional to what? Correct?
Yes, sir.
And N is proportional to what?
Sir.
Correct?
Yes, sir.
Therefore, VV plus will be proportional to what? F
half order of Fermi direct integral.
divided by
N.
n. And what is n proportional
Acha,
to?
yes, sir.
Okay, that's the basic idea. So the velocity, injection velocity will also be dependent on the Fermi integrals.
Yes, sir.
Okay, but the velocity will always be a, what to say, like ratio of two integrals. Current, charge, conductance, these are all single integrals. The velocity will be a ratio of two integrals. Again, to find out what two integrals will appear, you just have to find out what I is, what n is, and I by n will always give me this velocity. Okay,
Yes, sir.
so again, at a finite temperature, the constant of proportionality is also derived. So this you will see in the lecture. Why am I putting a star? This you will see in the lectures. So this is essentially v plus x. So this will be written as square root of 2 kBT by pi n star. So this comes from Maxwell-Boltzmann statistics, because at high temperatures the Fermi-Dirac distribution can be approximated by the Maxwell-Boltzmann distribution. So because of that, you can make this approximation into the ratio of the Fermi-Dirac integrals. So f half eta f divided by f half, sorry, f0 of eta f. All right,
Yes, sir.
wonderful. So now let us look at some of the properties of this. This average velocity, will it change anywhere in the channel?
Sir, no, because
Exactly, it will not,
the average.
because of ballistic transport.
Yes, sir.
So, it does not change in the channel. Why? Because ballistic transport. Therefore, where is this velocity achieved? Where in the channel is this velocity achieved?
Sir, where the electric field is maximum.
Not maximum, where the electric field is zero.
Ha ha.
Okay, so it is achieved at x equal to 0. So this velocity is achieved at, so now do you understand why I introduced the x equal to 0 concept before?
Yes, sir.
Okay, so this is achieved at x equal to 0, and this velocity therefore is called the ballistic injection velocity. So let me just write that in a lower line, that is bumping into the equations. So therefore this quantity Bx plus is defined as ballistic injection velocity. Okay. Now, why am I
Yes.
calling this the injection velocity? Essentially, they are pushed into the channel with this average velocity.
Okay, sir.
Okay. Now, is this quantity a function of temperature? Of course, it is a function of temperature, as you can see from here itself.
Yes, sir.
Do the Fermi integral contain any temperature dependence?
Yes, sir. Because we have considered eta is equals to E by
Very good.
kBT.
Correct. Yeah, you're right. Okay, so temperature dependence is there in both these parts. So, yeah, now we have what, like some 5 to 10 minutes left. So, um, we shall talk about the last topic of our discussion for today, and that is, now this looks very nice, correct? Like, I mean, the by nice I mean it is easy to understand. Like, there is a point where electric field becomes zero, so at that point a ballistic velocity is achieved, and the electrons travel with that same velocity until they reach the uh,
Great.
channel drain interface, and after
Yes,
that
sir.
some energy change, like energy exchange happens, and the electrons are, they migrate into the drain. So
Yes,
the
sir.
picture is pretty nice, and there are no collisions. So the velocity should keep increasing, right?
Mm,
Like, as and when I'm increasing the VGS, I should keep getting more and higher and higher and higher and higher, like carrier velocities.
yes,
I
sir.
I should never have velocity saturation.
Yes, sir.
But if there is no saturation, then how can it be a transistor? I need a
Mm,
linear region and a saturation region, right?
yes, sir. We need.
So how do we do that? So that is what we shall see in this final segment. So that is called velocity saturation in a ballistic MOSFET. So essentially what happens is, so are you familiar with the Maxwell-Boltzmann distribution? So essentially, let me just write it like probability. So like I will illustrate the concept of the velocity saturation using the Maxwell-Boltzmann distribution, but the same logic also applies to the Fermi-Dirac statistics. So Maxwell-Boltzmann distribution. So over here, f of e is given by e to the power minus e by kbt. Is this clear? Like, this is the distribution function.
Okay, sir.
So let me call this FMB, Maxwell Boltzmann, to distinguish it from the Fermi-Dirac function. Now the
Yes.
energy E can be written as half n star into Vx square plus Vy
Yes, sir.
square for a 2D channel. Therefore, this implies FMB of Vx comma Vy can now be written as, of course, there is going to be some constants over in this integral, in this distribution function. I'm not going to worry about the constants right now. I'm just going to write the quantity 1 by 2 m star divided by kbt into vx square plus vy square. Is this clear?
Yes, sir.
Now, what is this quantity? Like this expression, are you familiar with this function? So this is a 2D Gaussian. Like, you know what a Gaussian is, right? Gaussian is e to the power minus x squared.
Okay, sir.
Okay, so now in terms of that, this is like I have two variables, vx and vy, and I have e to the power minus some constant into vx squared plus vy squared. So this is a 2D Gaussian function.
Okay,
So
sir.
2D Gaussian function essentially, my God, this is the thing I've been dreading all along. Drawing 3D graphs on a board. So essentially, what will a 2D Gaussian look like? So a 1D Gaussian will look something like this. It rises and falls, right? It's a bell-shaped function.
Yes, sir.
Okay, like it's something like this. Okay, so our 2D function will be the same Gaussian essentially rotated. So what we are going to have is a, like, essentially we are going to have, yeah, something like this. And similarly, like this thing will extend itself to, yes, all the quadrants. Yeah. Oh my God, this is torture. Yes, so it's going to be like some kind of an elliptical shape. And you know what? The base is actually not important. What is important to see here is that, yeah, in fact, I don't even have to draw the axis first. I can just draw the curve. It is essentially going to look like this, but this tail is kind of going to rotate, like, yeah. So it's going to look something like this. So it's going to look like a hat, essentially.
Okay,
So,
sir. It's
okay, so
understood.
yes, so we are going to have like a circular base or an elliptical base at the bottom. So it's going to be something like a hat or like a cone, but the surface is going to be a lot more curved. So we are going to have a graph something like, so if I'm going to draw this like this, then around this base, my top is going to look something, okay, not so distorted. Yeah, I think I can use one axis for reference. Yes, so across this one axis, I will draw one Gaussian. And yes, we have a base for this Gaussian, something like this. Yeah. So is this part clear?
Yes, sir.
Okay, wonderful. The sooner I'm done drawing this, the better I will feel. Okay, so there is this now. Of course, the the z-axis here is actually this f function, and in the base we have the xy axis. Yes, now this makes much more sense. So we will now have the x-axis over here and the y-axis over here. Okay, and the
Yes, sir.
z-axis will be the function. Now remember that in a ballistic channel, no matter how transport happens, the number of charge carriers present in the channel is a constant given by the
Yes,
charge
sir.
integral. Correct?
Yes, sir.
So what will essentially happen is, so now see, you can actually see that x is varying in positive and negative direction, y is varying in positive and negative direction. So what does that mean? So essentially this axis is not the x and y axis, this is the vx and the vy axis. Like, because those are the variables here. Is that clear?
Yes, sir.
Okay, so this is the Vx and the Vy axis. So this is the Vy axis and this is the Vx axis. That implies for positive Vx, the electron is moving in the positive x direction. For negative Vx, the electron is moving in the negative x direction. For positive Vy, the electron is moving in the positive y direction. And for negative Vy, the electron is moving in the negative y direction. Is that clear?
Yes, sir.
Now, as and when I keep increasing the applied potential, what will happen to this graph? More and more electrons will start moving in the desired direction, correct?
Yes, sir.
And the desired direction for us is the positive x direction,
Yes, sir.
right? So what will happen is, if I consider a plane, that is why I drew the axis in red. If I consider a plane cutting this thing in half like this, okay, across this, like the
Yes, sir.
x-axis, more and more electrons will jump from the negative side to the positive side.
Okay, sir.
Like they will, like more and more electrons will start gaining a net positive Vx.
Okay, sir.
But because of our like ballistic condition, the number of electrons that can be present in the channel is a constant. Therefore, after a certain point, there will be no more electrons to come from the left side to the right side. So after saturation, so essentially at saturation, what will happen is, essentially, let me draw the axis like this, and let me draw the plane that is cutting, and let me identify the blue line. This is the function, like the velocity distribution function. So essentially what will happen is, everything like to this side of the plane where Bx is negative, there will be, the probability will become 0. So this is Vx and this is Vy. So the entire velocity distribution will be only on this side. So what you will essentially have is a, uh, how should we draw it? So rather than looking, yes, the better option will be to view it in the opposite direction, like view it from the other side. So in that case, what will happen is, I'll have to draw the axis like this, yes, and call this the x-axis or the vx-axis, and this will be the vy-axis, and let me draw the plane like this. Yeah, yes. What will essentially happen is the Gaussian, which was previously symmetrically distributed across this plane, will be entirely on this side of the plane. So this function will be totally flat on this side, and it will only start falling on this side of the axis. Is that clear?
Yes, sir.
So for a more like precise presentation, representation, it should look something like, where is velocity saturation? I think ballistic injection velocity will have that. Yeah, so it will look like this. Is this clear? Initially, there is
Yes,
a
sir.
Gaussian, and as the electric field increases completely, one half of the Gaussian will totally move to the other half.
Yes, sir.
So as you keep increasing VDS, this is what happens to the velocity distribution. So after a certain point, there are actually no more charges to contribute to the increase in the velocity.
Yes, sir.
Like there is literally no more charges. Since there
Hmm.
are no more charges, the velocity cannot increase any further.
Yes, sir.
And that is why saturation occurs in a ballistic device.
Hmm.
Okay, so velocity saturation is essentially what leads to the saturation mode in a ballistic device. So with that, we come to the end of today's discussion. So these things should help you understand the concepts that are being discussed in the lectures,
Okay, sir.
and should also, subsequently help you solve the assignments. So yeah, with that, I suppose we can bring today's session to an end. If you have any questions,
Yes,
of course, you can ask me. Uh, if there are no questions, I think we can end this session.
yes, sir. We can end the session.
We can end the session, right? So, yeah, in conclusion, so the things that one has to remember are everything, every calculation that we are doing for a MOSFET. So, let me just minimize this and stop presenting. Since, yeah, Kumar seems to have yeah. Yes. So since Kumar has had some network issues, so the concepts that need to be remembered are ultimately the current and the charge stored in a ballistic device are still represented by the original integrals that we had discussed in the first half of the course. However, the internal distribution of charges and the energy levels are determined by essentially what is the channel electrostatics that we shall take care of in our next week's discussion. Um, but insofar as the transport is concerned, yes, the ballistic transport equations that we discussed in terms of modes and the Fermi-Dirac integrals are still applicable. Depending on the energy dependence in these integrals, one can easily determine what kind of Fermi integrals will be used in that particular quantity. So the quantities that we discussed are current and stored charge. By dividing the current flowing through the channel divided by the charge stored in the channel, we get the notion of the average velocity, or what is known as the ballistic velocity, average ballistic velocity of the electron. And by using the previously defined concept of the zero electric field point, we identify this velocity as the ballistic injection velocity into the channel. And the Fermi integral ratios for that was also seen in today's discussion. Finally, in the end, we gave a brief notion of the concept of velocity saturation in a ballistic MOSFET to illustrate the concept that even though carrier transport occurs in a MOSFET channel, in a ballistic MOSFET channel without any collisions, electrons do travel in a ballistic fashion. But in theory, it is not possible to raise the velocity of the electrons beyond a certain limit. The reason for that is because there are only so many electrons present in the channel, and that number of electrons will have to be present no matter how high the current goes, because that quantity is a constant. We derived that as a constant quantity under equilibrium conditions.
Yes,
So
sir.
that essentially places a constraint on how fast the electron can move through the channel. So ultimately, that will lead to what is known as velocity saturation. And since charge times the velocity is the current, that will also give us a current saturation. And this saturation is what we observe as the switching from the linear mode to the saturation, like linear regime to the saturation regime of the MOSFET. So that summarizes the concepts that we have discussed in today's session, and this should help you by and large to solve the assignment questions. Um, with that, we conclude this week's session. We shall meet again next week, same time. I thank you all for listening and attending. So I'm ending the call and
Thank you, sir.
stopping the recording. Yeah, yeah, you're welcome.